So here we showcased a proof of concept of a locking device that we printed. At first we were intending to use this to support a abdominal aortic aneurysm, which happens in aorta, to print this flow model having like a dilation in its outer diameter, and supporting it with this locking structure, with a shape fixing it, then inserting in open surgery, and when it twists around the tubular organ, it can be locked and support the blood vessel. We showcased this in animal too, but we didn't move on to other survival surgeries because we were intending to have like a minimally invasive design. So as a proof of concept demonstration of a minimally invasive design, we started our collaboration with Dr. Talley at the University of Minnesota. It was a very valuable collaboration. I'm going to show more results with them in next slide. So they provided us with a CT scan of an AFib patient having the left atrial appendage here. We designed this left atrial appendage based on this 3D CT scan. Then we also used a portion of the heart to 3D print it with another material to have like a flow model and show the proof of concept of deployment of our medical device inside this portion of heart of the patient through a catheter. So with that result, we concluded the whole first phase of the studies. Achieving high biocompatibility in cell studies. In vivo results of vascular grafting in mice showed high potential for tissue regeneration, and we could also showcase a proof of concept of an left atrial appendage occluder in vitro. So the third objective was to design and develop like the third generation of this material, PGD-based shape memory polymer. And here we wanted to add the multi-transitioning properties and also the onset recovery property that we observed in the Nature paper. Here, the motivation of this phase of our research was to endovascularly embolize or occlude a blood vessel or aneurysm. So we picked aneurysm occlusion because like embolization can cover a very vast area in interventional radiology, even letting us to treat tumors. So here first, what is aneurysm? It's an abnormal dilation in blood vessel, typically 1.5 times larger than the normal size. It commonly happens in arteries due to high pressure, and it is less common in veins due to lower pressure. It has different risk factors, and a key statistic about aneurysm is like each year 2,000 people in the US get abdominal aortic aneurysm. 6.7 million people in the US have an unruptured brain aneurysm. Most of them are asymptomatic, and like 30,000 people get brain aneurysm rupture that can lead to death. So here, first I want to go over the literature, the state of art of embolization devices published in Biomaterials, Advanced Materials, and Advanced Functional Materials. The first one is water triggered. It showed minimal swelling. We want to maximize the swelling to increase like the rate of occlusion. They didn't show any control recovery. As you can see in all these studies, the recovery happens in less than a minute. So this is kind of intuitive. Maybe they think that they want to achieve the highest shape recovery profile, but the reality is we want an optimal shape recovery profile, because like in reality at the OR, doctor needs some time to deploy the material, to transfer the material through the catheter. We don't know how many turns this catheter is going to go inside the vasculature to reach the target. So this can cause immature deployment inside catheter, this a little time. So we want an optimal time and no more complications. So the second study showed thermal trigger 27 degrees C, which is not compatible with body temperature, but they showed survival surgery for 12 weeks, which is a very valuable data. Here they showed thermal trigger 38 degrees C, which is proper for bodily deployment. Their clothes were personalized, but they were not using 3D printing, 4D printing. They were using molding, and they couldn't achieve high packing density. They also had a very valuable animal model for induction of Sackler animal model in rabbits that we are going to use in the future studies. So the goal here was to develop a disruptive 4D printing system to fabricate highly complex micro-resolution coils ready to implant endovascularly in MIS techniques. The first goal was to maximize printing resolution to micron scale to enter the realm of microcatheters. We wanted to induce double transition temperature and make the material adaptive to four different environments. For example, from OR to the catheter, then blood vessel, and finally final swelling and deployment. And yeah, we wanted to increase the rate of occlusion and increase the packing density using computer-aided design.